And so this is our binary number, 1, 0, 0, 4 zeros, and then another 1, and then 0.111. Actually, that's a pretty easy integer to figure out what it is. Right now, looking at this integer, is it even or odd? You should be able to tell me a binary is even or odd just by looking at it, first glance. It's odd because it has the ones place. Yeah. Okay, so if that 1 is ever in the ones place, you know it's an odd number. Right? So that's what I always think when I see the 1 there. So we go 2, 4, 8, 16, 32 plus 1, 33. So remember when you're doing these, you do your integer part, and in your computer, your integer part is stored separately than your decimal part. So in a double number inside of a programming language, the integer part is stored, and then the decimal part is stored. Okay, they are stored separately. Okay, so looking at your textbook here, on figure 21 in chapter 2, they give us an example of how a double variable or a fractional variable that we have would be stored inside of a computer. So in this example, they say that the first bit will be a sign bit, saying if it's a negative number or a positive number. So 1 is for negative and 0 is for positive. And then they have this exponent part and this significand part. And to better understand what these two parts are, let's look at this example. Let's say that we're going to store a positive number 17 inside of our computer. When we translate 17 to binary, we see that its binary representation is 1, 0, 0, 0, 1. So it's the 2's place, the 4's place, the 8's place. The 16th place has a 1 in it, and the 1's place has a 1 in it. And we see that that is indeed the binary representation of the number 17. So it's this number to the base 2 times 2 to the 0th power. That's another way of writing that number, because 2 to the 0th power is 1. Now if we take that binary number and we move the decimal in the binary number over 1, we would have to multiply that number times 2 to move the decimal back to where it was. So another representation of this number is to represent it with a decimal floating point. So not to get it confused with decimal numbers, we'll call this a floating point. So your floating point moves over left 1. You'll have to multiply this number times 2. So 2 to the first power is another way of writing that, to move the decimal back to where it was. So it is the same exact number. If we move the decimal place over again, we multiply by a larger power of 2. One more power of 2 to move the decimal place back over to the right. And we can keep on with that kind of logic and move our decimal place so it is to the left of the first 1 value inside of our number. So this is the number 17 with the decimal place moved over 5 times. So it's the same number as this number over here, but now we have to multiply it times 2 to the 5th power because we moved that decimal place over to the left by 5. So when we do this, this is our significand. Everything to the right of the decimal place is our significand. And this number 5 here is our exponent. So when we store this number inside of a computer, this is how we're going to store it. Let's see what number this is. 2's place, 4's place. So it's 4 plus 1, that would be 5. This is our exponent. This is the exponent for the 2. Now over here for the significand, we can see that this is the 1, 0, 0, 0, 0, 1. And we see that's the significand right there, a direct representation. It says using this form, we can now store numbers of much greater magnitude than we could using a fixed point representation of 14 bits, which uses a total of 14 binary digits plus a binary or radix point. So let's look at an example for this. So they have an example here that says let's try to represent this number here, 65,536, using this methodology of having our exponent and our significand. So what we do is we take this number and we translate it to its binary representation. And we can see here in the calculator, when we type in this number, its binary representation looks like this. 1, and then a set of 16 zeros after that 1 is the binary representation of this number. So using that methodology of moving our decimal place to the left and then multiplying it by a power of 2 to the number of places we move that decimal place to the left, we would have to move the decimal place 4, 8, 12, 16, 17. We'd have to multiply by 2 to the 17th power or move that decimal over 17 spaces. So our significand will be 0.1 and then the rest zeros, and our exponent will be 17. We can see that in our example here. Our significand is 1 followed by a bunch of zeros, and our exponent is 16 plus 1, 17. Our sign bit is 0 because it is a positive number.
We know that the integer part is 33, so now we just need to figure out our decimal part and translate it to decimal. Or you can do how we did here and just the 2, 4, 8, 16, 32. What is this one? It's 1. Yeah, it's 1/2. It's 1 over the power of 2 to the first power. Okay, so this will be 1/2 plus 1/4. So we're doing the same thing, 2, 4, 8, and just putting it underneath the 1. Okay. And then if you're like me, I kind of like just to think about it as fractions. You could convert it to decimals and add them up. This would be 0.5 plus 0.25 plus, what is that one? Yeah, 0.125. Okay. So you could do it that way. So you could say 0.5 plus 0.25 plus was it 125? Yeah. And then add it up. Okay. Another way that you could do it would be to convert all these to the same denominator. So this would be 4 eighths plus 2 eighths plus 1 eighth. Would be 7 eighths, right? And then the same thing here. That one would be 0.875. So there's lots of ways you can think about it. It's good to think about it in its different forms. Remember, they're all saying the same thing. They're just in a different form. Okay, so they're all giving you the same answer. So then our answer would be 33.875. I think this is the important part with this kind of problem is knowing that you convert your integer part separate than your decimal. That's the only kind of thing that you really have to remember there. Okay, all right. Let's look at number 34. Someone actually asked about 34. We can do one of those. We have an 8-bit binary number, 0111, 0101. And 00111, 011. And we're subtracting. So remember in your computer doesn't actually ever subtract, right? It only can do addition. And remember that what it does is it takes this number, sees that it's negative, and applies the 2 complement when it stores this number. And then it adds them using the 2's complement, okay, which is easier than borrowing. Okay, and your computer doesn't borrow because it was too hard to implement it in hardware. Remember, that was the reason. Okay, so what we could do is we could take this number here and convert it to its 2's complement. Okay, So it would be a 1, 1, actually, well, I'll just convert it here. I was going to rewrite it, but, so you just take all the zeros and turn them to ones and all the ones and turn them to zeros. And then you add 1. That's how you take the 2's complement. So it would be 0, 0, 1, 0, 0, 0, 1, 1. And then we add that 1. And that is this number in 2's complement form. Okay, so now we can use addition. So now we can add this number to that number. It is as if we're subtracting it. Okay. So then we add those two numbers up. And 1 is 2. Good. It broke you from saying 10. Okay, so then 1 plus 0 is 1. 1 and 1 is 2. 1, 1, 2, 2. And then what do we do with the overflow? Do you guys remember what we do with overflow? So this was an overflow bit, right? Because we had 1 and 1, it was 2, and then we carried that 1 and he was over here. What do we do with our overflow? Anyone? Yeah, we throw it away. He's ignoring it. So. And there's our answer. Now we can see if this is really our answer. You could go online and see. But you could also just translate these to decimal and see if that's the right answer. So what number is this? This would be 2, 4, 8, 16, so that'd be 20. 20 plus 32 is 52. 52 plus 64 is what? You guys tell me. What's 52 plus 64? 6. 116? Because we should get the same answer at the end if you translate these to decimal. Okay, because remember that this is the same number. We're just representing it differently. Okay? And I did that right. You guys are checking me, right? Hopefully. So we know this is 3. Okay, plus 8. That'd be 11. Plus 16. That would be 27. Plus 32. Would be 9. Would be 59. And what is 116 minus 59? You guys tell me. You're going to make me multiply this out. Okay, 57. All right, so this guy better be 57, right? That's how we check ourselves. So this would be 2. You guys realize what I'm doing here. I didn't write it down because I've been adding them in my head. But you just add in all the ones that are in the place values. So it'd be 2, 4, 8, 16, 32. Let's see, that would be 10, 26 plus 32 would be 58. So what did we do wrong? But what did I do? Oh, was it 117 up there? Oh, yeah, because it's odd. Yeah, that should have been a telltale sign that I did something wrong, because here he has a 1 here, and I said 116, but he should be 117. Okay, so then we'll get the right answer. Well, right here, this is actually 117. Wait. So 7 plus 9 be a 6. And actually, then what did we do wrong here? Did I translate this wrong? No. 2, 4, 8, 16, 34. And the answer is 0, 0, 1, 1, 1, 0, 0, 1, 0. We must have translated something wrong here. Because this is the answer that they gave me. This was the right answer. So we did this part right. But maybe we did this part wrong? Right here? What is it?
No, the answer is 2015.
Oh, because I was subtracting and I added in my head. I did 7 plus 9 instead of subtracting. It was 17 minus 9. And so you do actually, okay, good. I was going to say, it should come out to be the same. Because remember, these are the same exact numbers, we're just representing them different. Okay? Right? So it is the same number. So we're all good on the subtraction. And remember that the most important thing about 2's complement is the positive number always stays the same all the way across. If it's positive, you only do the ones and zeros, zeros and ones, and add 1 when he's negative. So this would be the positive 2's complement of this number. And this is the 2's complement of this number. Okay, so these are both in 2's complement form. All right? That's probably the most important thing. And then let's do a multiplication problem. We can do it both ways with the algorithm and then just regular multiplication. I was just looking on the video. It's mostly showing up on the video today. Like maybe we can move that. How's that? I'm learning. Okay. Yes. Okay. So let's see here. We're going to do, was it 36? 36. All right, so we have some multiplication problems. Let's do letter B. So this is 36B. And it says 10101 times 111, which is 7. And it tells us that our answer is 100100011. So, two ways you can do it, right? You can just multiply it, which is actually pretty easy because we're just multiplying by 1 or by 0. So then remember to shift. And then you add them up. So it'll be 1, 1. 1 plus 1 is 2. 1 plus 1 is 2. 1 plus 1 plus 1 is 3. And remember, 3 is 1, 1. Represented by 1, 1. And then 1 plus 1 is 2. And 1 plus 1 is 2. And then what do we do with the overflow bit? Actually, they left it on our answers. We leave him in. All right. But we should check this thing too. It is good to translate and check these things. So this would be times 7. And what number is this? 2, 4. 4 plus 16 be 20, 21. So isn't it getting easier to translate these binary numbers in your head, the small ones? Yes, it should be getting easier. Okay, then this would be 7 and then 14. This is an odd number, so it's looking good already, our answer. But just to check it, this would be 2, 4, 8, 16, 32, 64, 128. So what would that be? Yep, 147. Cool. So then you can always double check yourself that way too. Because remember, they are doing the same exact thing, they're just representing it different. Okay, and the only reason that decimal is easier for us is because we're used to looking at it. Plus, I think it's a lot of ways easier too because it is hard for our minds to look at ones and zeros. It is hard because they are all kind of the same and they start to blend together.